Okay, so Patrick already talked a lot about this, what a polygenic score is. It's basically an index that aggregates the estimated effects of individual SNPs. And well, we can consider it as a measure of genetic propensity towards a trait, basically. I'm going to pass something.
It reacts slowly. If you look
Okay.
at my laptop, then it won't be as slow.
Okay. So what you need to construct a PGS, you need this GWAS summary statistics from a discovery sample, and you need the individual level genotype data from the prediction sample. As Patrick also mentioned, you need to make sure that the prediction sample is not in the discovery sample. Otherwise, you'd be overfitting. And yeah, so there are mainly, methodologies mainly differ across 2 dimensions. One of them is how you generate the weights that you use to construct the score. And the other is how you determine which SNPs to include in the score. The 2 most common methodologies are, well, one is pruning and thresholding, which is probably what you know about. And the other one is LD-PRED. That I'm sure there are other methodologies, but these are the ones that we're going to talk about. So in pruning and thresholding, you set the weights equal to the GWAS estimates of the SNPs. So you just use the betas from the GWAS, and then you select the SNPs based on a pruning algorithm to make sure that there's not double counting of causal SNPs. And you also apply a p-value threshold. So you want to, well, you can at least omit SNPs whose p-values are above a certain threshold. So this is, of course, done to boost the signal-to-noise ratio. You want to include the SNPs that are more likely to be associated with your outcome. And the pruning is, again, done to avoid the double counting. So whether to include all imputed variants or only genotyped variants in PNT. So this kind of depends on how many genotyped SNPs you have. So it depends on the genotyping chip. If you have 2 million genotyped SNPs, they're usually sufficient to actually have enough coverage. If you have 300,000 SNPs, it may not be that good coverage. So you may want to actually also include imputed SNPs there. It also depends how well your variants are imputed. So if there are a lot of badly imputed variants in your data, you wouldn't want to include those because there would be a lot of uncertainty about the genotypes, and then, well, you'll have a lot of additional noise. So, I mean, in my experience, it's usually better to stick to genotyped SNPs if you have enough of them. Otherwise, if you have like very few genotyped SNPs, though, still imputed SNPs are a better option. If you're including imputed SNPs, it's also a good idea to impose an imputation accuracy filter so that you don't include the worst imputed SNPs. But, well, I mean, what the imputation, yeah?
Is that filter in both the discovery and the target? Or?
This is just the target. So I'm assuming that we are dealing with meta-analysis results. And then since that is obtained by meta-analyzing a lot of cohorts, we don't have imputation accuracy values for those. Yeah?
Do you have a rule of thumb for
the filter?
How many is enough?
Well, so I mean, in HRS, for example, there are 2 million SNPs, and that does the best, the genotyped SNPs. In the Swedish twin registry, for example, we have less, and their imputed variants actually do better. So I would say something like, I don't know, 1 million SNPs would be enough, probably. Less is probably going to give you worse than an imputed SNP score.
Of course, all of these things are heuristic,
yeah.
so sample size dependent, right? So it has to be the case that at some end, eventually those less well imputed variants are going to add some predictive power if you handle them appropriately. It just doesn't, we just don't appear to be there yet, right?
Yeah. Okay, clumping or pruning. How do you select your SNPs? So Patrick also again talked a little bit about this. You talked about pruning, I think.
I think I used the word
Yeah, yeah. So what the difference between the two is that clumping is basically done using the p-values. So you have your GWAS results, you have your p-values, and then you take the most significant SNP. You look at the SNPs that are correlated with them, with that SNP, and then drop them if they're correlated, and so on. So it's phenotype dependent, basically. You try to get the most significant SNPs out of all SNPs. Pruning is blind to the p-values, so you don't use the p-values at all. You just have a reference sample, and then you use basically you get the independent SNPs using LD from that reference sample. But since you don't use the p-values, it's likely that you're losing a lot of causal SNPs. So this is actually very straightforward. Clumping is better.
It's not. Yeah, I mean, it's not clear that it necessarily would be though, just because with clumping, you're selecting on the most significant ones, and so you're going to be more affected by winner's curse. But it's just that those concerns seem to be a lot less important than the concerns of dropping
Causal SNPs.
SNPs.
Yeah. Clumping parameters. So you need an R-square threshold and an LD window to do the clumping. The R-square threshold is basically the threshold that you choose over which, if your SNP is correlated with your index SNP with an R-square of more than 0.1, for example, you drop those SNPs. So 0.1 is the threshold that we use to clump the GWAS results, because we want to be conservative and we don't want to look like we're basically reporting more SNPs than we have. But it's actually not very useful in constructing scores. So you are dropping a lot of SNPs that might be actually different signals. So in prediction, when you're constructing scores, in my experience, usually 0.5 to 0.7 gives the best results. Again, this is heuristics, but 0.1 is definitely too low, so you don't want to go as low as that, I don't think. LD window. So, and that LD window is the window that you look at around your index SNP when you're deciding whether the SNPs in that window are correlated with your index SNP or not. So the danger of choosing too large an LD window is that your reference sample is not perfect. So it's not, it has a limited sample size. So there could be errors in the LD estimates, and it could look like apparent LD whereas it's just noise. If you're looking at too small, yeah.
Excuse me, the 0.5 and 0.7 recommendation is mostly for European ancestry samples or applies to other groups?
Yeah, I've only looked at Europeans, so yeah.
You'd think it would be kind of like the same thing, because the principle is that there's a trade-off, right? On one hand, you want to throw out SNPs that are too highly correlated to limit double counting. On the other hand, you want to keep as many SNPs as possible because they contain more information. And so I'm not sure why the R-squared threshold would be ancestry dependent. It's like that kind of window is the one where those trade-offs are seem to be balanced.
So it shouldn't be ancestry dependent.
I would think it would be. I mean, ultimately, you should all be doing LD pred.
Yes.
But
We're going to get there. I mean, even if it varies a little bit, I don't think it's going to really matter much. Like, it should be the same, yeah. Okay, so LD window, yeah. If you choose too small a window, of course, there could be like high LD regions that are very long, and well, those SNPs are going to look like they're independent to you because you're not looking at far enough. But they would actually be dependent. So my recommendation there is 1 megabase. That usually works. And it's not too short, it's not too long. Yeah. So next, thresholding. Thresholding is again selecting the p-value threshold above which you're just going to not include SNPs that are not likely to be associated with your phenotype. The optimal threshold there depends on, first, the polygenicity of the trait. So if your trait is very polygenic, like educational attainment, there are going to be a lot of SNPs associated with it. Not all of them are going to have very low p-values. So if your trait is really, really polygenic, you want to choose a very high p-value threshold. it also depends a little bit on the sample size of the discovery GWAS, because if you have like a GWAS on 10,000 individuals, nothing's going to be significant, for example, and you're not going to have any SNPs below genome-wide significance, so you're not going to predict anything. But then again, I mean, it's best to, of course, not construct PGS using underpowered discovery samples. So for polygenic traits, we usually do, for educational attainment, for example, P equal to 1, which means like include all SNPs in the score. Yeah.
Just wondering, I noticed that you mentioned over here that the optimal threshold also depends on the polygenicity of the trait. Would you say the same argument holds for the LD window also? Because one reasoning is that you are, maybe one way to think about it is that you could have two SNPs in close LD, but both of them have independent effects. And I'm guessing that's more probable if you have highly polygenic traits.
Yes, but so, and rather than the LD window, maybe the R square.
Right, exactly.
Yeah.
Yeah. Okay. So I guess that
Yes.
you would say that's also, I guess, trait dependent.
Or LD pred. Problem solved.
Yes.
It doesn't need to be tried. So it's more to know these things because you'll see these in a lot of places, and a lot of people will say, "Oh yeah, we pruned or we did this," and so these are some of the considerations that you should be thinking about. But in your own research, you should almost always be doing LD pred. It's just
Yeah.
better
It's better.
because we don't lose. When you start pruning, you're just throwing out so much information.
Yeah. Okay, so this is a plot showing the predictive power for different R square thresholds in clumping, different p-value thresholds. And I don't know whether you can read it in the back. So the green bars are genotyped SNPs. The orange bars are imputed with an imputation accuracy threshold of 0.9. And the blue bar is all imputed SNPs. So here, this is HRS. So again, they have a lot of genotyped SNPs. So imputed SNPs don't really add anything. But p-value, and the trait is educational attainment. So the takeaway message from this is that you need a high p-value threshold. It could be a little bit lower than 1, for example, as well you can see in the in that here, basically here. But since you don't know what exactly that optimal point is going to be, I would just choose p equal to 1 and include everything.
What's the meta-analysis sample size for these results?
This is,
It's like 700-ish.
I think this is like what we have right now, 750K.
I thought it was higher. I think it was more like 9% in the HRS. Right?
That's an LD
This
pred
is-
though.
Yeah.
Oh, that's LD pred. I see.
So
Okay,
this is
got it.
pruning and thresholding, yes.
Are you going to have a figure of what this looks like for height, for example?
No.
So if you do this for height, it's like an inverted U shape where you get the maximum somewhere in the middle.
Mm-hmm.
And of course, eventually, that's what's going to happen to education too. But so far, apparently, when you add SNPs that are barely significant at 5% level, you're mostly adding genetic signal. Enough genetic signal to cancel out the noise.
I think there's actually a lot of confusion too. So I think a lot of people, they say, oh, we're making a polygenic score, and so they're like, well, I only want to do the score on the SNPs that are significant, and because those are the causal SNPs, right? And so they'll make a score just based on the genome-wide significant ones, but that corresponds to the far left bar.
Yeah.
And so if they do that, you say,
yes,
no,
this-
it's too wasteful, there's too much information, and even though we're probably including SNPs that are not associated when we have a much less strict p-value score, the signal to noise ratio, we're adding more signal on average than we're adding noise, and that's why we're seeing an increase in general as we relax the score.
So on average, as the sample size gets bigger, that's going to go pushed further
Yeah.
and further left, and at n equal infinity, you just should be using the
Yeah.
genome-wide significant SNPs.
Yeah.
Oh, we just
Uh,
make that
or
up,
yeah.
Right? Or the beta hats,
That's what you're using 0 for those.
because there is no
Yes.
p-value.
Yeah.
Yep. So this is, again, the x-axis is different p-value thresholds. It's with different clumping R square values. So green bars are R square equal to 0.1. Orange is 0.3. The reddish one is 0.5. Blue is 0.7 and yellow is 1. So as you can see here, yellow is the worst. So if you don't do any clumping, if you double count everything, it's going to do much worse than some clumping. And still, R square equal to 0.1 is not doing that well compared to the others either. So then you're dropping too much information, you're dropping too many SNPs. So something in between is usually good.
So can we go back? I'm sorry to keep asking
Yes.
questions, but this is something I'm curious about. So I'm just trying to think that, no, the last one, the one right there.
Yes, here.
This gets to my question I'd asked a second ago.
Mhm.
But I mean, just conceptually, if we, I mean, I don't think, here's my contention, I'm not sure this is right, but I think that if you have, I think the problem isn't so much double counting as it is you have unequal double counting across the genome. And so if you've got, you know, the same exact, you know, all these SNPs are in LD and are, you know, the same amount of LD and there's kind of the same amount of SNP density across the genome, then I don't think it actually matters much. I think the problem is that you're counting some regions a lot and counting some other regions very, very little relative to what they should be
Yes.
counted. And so you've got this extra noise being added into the PGS. Is that
I think so.
is that right? Or you
Sounds right.
I mean, if you think about it, just, you know, doubling up the number of SNPs you
it'll
have,
do nothing.
it's going to do nothing
Yeah.
to your PGS, right? And you're double, and there you're exactly double counting every SNP.
Yeah, I mean, yeah, if you had pairs of SNPs that were all perfectly correlated, I mean, there could be some funny nuance if there's variation in the effect sizes, and then, you know, and then imperfect genetic correlation. Imperfect correlation between the SNPs. But yeah, but I think in general, the general idea, I think you're right. Like variation in these things means that we're going to be off by not just a constant factor, and that's
Yeah.
what causes problems.
Okay.
And LD pred. So I'm going to pass these. Patrick already explained what LD pred does. So here, the decision of whether, yeah.
Sorry, just get back to the previous slide for me. So one thing that Patrick didn't say is what you need to tell LD-pred and what LD-pred is going to estimate for you. So that might be worth.
You mean the posterior, what do you mean?
So what are the parameters that you would have?
Yeah.
I'm gonna, so these are the, next slide. So here, to decide whether you want to include imputed or genotyped SNPs is a bit more complicated, because LD-pred uses a reference sample, individual level genotype data, to estimate the LD between SNPs, and then it adjusts the betas using those LD values. So that means that the SNPs that you want to include in the score also need to be in the LD reference data. And so you want to estimate the LD, of course, using genotyped SNPs. So you wouldn't want to estimate LD using imputed SNPs because those are already, and there is some uncertainty at the genotypes, and it's not really optimal to use imputed SNPs to estimate LD. So unless you, if you want to include imputed SNPs in your score, you either need a large and representative sequenced sample, which is not really always available, or you need to use hard-coded genotypes. So you need to convert dosage data, imputed dosage data, to hard-coded phenotypes, that is genotypes. But that, again, as I mentioned, introduces extra noise.
Can you explain what those terms mean? I don't think.
Hard-coded?
Hard-coded versus.
Yeah, so
this.
hard-coded genotype, well, that's basically you have the dosage data, you have the genotype probabilities after you impute your data. So certain probabilities assigned to, for example, the AA genotype. AB genotype gets something else. And then you basically just take there are a couple of ways to do it, but you take the genotype with the highest probability and assume that's the genotype. So that's hard calling the dosages. So since it's not the probability of that genotype being the actual genotype is not 1, you get a lot of additional noise there when you estimate LD using hard-coded genotypes. So in the LD-pred paper, they suggest using the directly genotyped data from your prediction cohort, or your validation cohort. That's kind of useful because you don't need additional individual level genotype data if you do that. But it may not be optimal, first, if the number of genotyped SNPs is very low. So if you have like 300,000 genotyped SNPs, you're just going to have that many SNPs in your score, which is not always really that good. I mean, it may not have sufficient coverage. Or it's a problem if your validation cohort has been genotyped using multiple chips. So that means you have, like, for example, 200 people that have 200,000 SNPs, and another 500 people that have 500,000 SNPs. So to construct, well, you cannot use the genotype data to estimate LD then, because you have to actually pool those data together, and for that you have to impute the data first, because, well, you need the same SNPs to be in both batches. So that gets to be a problem. Or if you want to do prediction in multiple cohorts, and if you want to compare the results, you would want the same set of SNPs to be in all the scores. And if the cohorts are genotyped using different chips, you're not going to have the same SNPs in each cohort. So then you may want to use imputed data. So the question is how you can minimize the noise resulting from the imputation uncertainty while still having sufficient coverage of the genome. You could include only SNPs with imputation accuracy above a certain threshold, so that your LD reference data is not that bad. Or you could, well, in my experience, this is the best thing to do, actually. So you could use HapMap3 SNPs. HapMap3 SNPs are usually imputed really reliably, and they do have enough coverage of the genome. So if you just, so you could just select HapMap3 SNPs from your imputed data and use those in the score and also to estimate LD.
We should explain. I don't think HapMap3 has come up previously, so that's
Ever?
That's it. No.
Okay.
So that's another reference panel besides 1,000 genomes, which has come up a lot. HapMap3 is actually the older one that has fewer.
It
SNPs
has
in
around 1 million SNPs, I think, 1.2 maybe. Yeah, so I mean, it's a set of SNPs. Basically, there's nothing else to say about.
And it's European ancestry only?
Yes,
How many
I think so.
No?
No?
It says there's like 10 populations.
Is it?
10 populations. But fewer
But European-
populations than 1,000 genomes?
Caucasian or?
Yeah, for sure.
Okay.
So why go to HapMap3 instead of 1,000 genomes?
Because
I saw like the NIH actually put down the website for HapMap because somehow there was some.
no, so what I mean by using HapMap3 SNPs is using the set of SNPs that are available in the HapMap3 panel. So you're just, I'm talking just about the SNP IDs that correspond to the HapMap3 SNPs.
So
So
those
the-
are always going to be well imputed, even if you want to compare 3 different cohorts with different.
You're still using 1,000 genomes imputed data, but since a lot of those SNPs are going to be badly imputed, you're selecting HapMap3 SNPs from that data so that you have a set of reliably imputed SNPs, basically. That's the point. So if you want to compare results between your 2 prediction cohorts or your multiple prediction cohorts, including only SNPs with imputation accuracy above a certain threshold is not very feasible, because in each cohort you're going to drop different SNPs. So that is not going to be very useful. So HapMap3 SNPs is always a good option. It usually performs nearly as well as genotyped SNPs, and sometimes better if you have very few genotyped SNPs. And it also takes much less time to run, so compared to all imputed SNPs or imputed SNPs with high imputation accuracy. Yeah.
The HapMap3 recommendation seems like it's going to be relevant also with, like, so they selected those SNPs because I think that they explain a lot of the variation that's relevant in European samples.
Yeah.
And so if you're taking your data into a non-European sample, the recommendation of HapMap3 may not be the right choice, because that subset of SNPs may not tag, like the tag variation enough of the variation in a non-European group, right?
Is it though? I mean, if it's like 10 populations in
It doesn't
HapMap3.
even look like the majority of the populations are not white.
Yeah, it's really weird group
So I don't think it's
Well, so
like
they have that information in those
Or ones
groups.
that are interesting.
But the question is, it's not whether or not we have reliable information on you know, how much the tagging is, but it's whether or not that subset of SNPs tags the set of omitted SNPs very well. And so I think that those SNPs are chosen to tag a lot, like the variation in Europeans, where there may be genetic variation that's not well tagged in African ancestry samples by HapMap SNPs. I don't know for certain, this was just me, that's my understanding.
I don't know for certain either. So
I think there are two separate issues with SNP selection. The first is that you want them to be well imputed because that's going to just, ultimately you're going to want a really precise estimate of the pairwise correlation. But then the second issue is that you want the estimates in your sample, you're hoping that those are going to be representative of the LD structure in the GWAS from which you get your coefficients. And it may be that HapMap 3 also compares, like, has favorable characteristics from that point of view. That maybe you know something about that, right?
no, so you mean that the HapMap 3 SNPs, the LD between HapMap 3 SNPs is very representative of
Could be, yeah. Could
European
Could be
discovery
that
samples?
Yeah, I mean, maybe it is, maybe it's not, but the representativeness is important for whether or not the LD pair is going to be
Yes,
any
yeah.
gains.
So I'm going to get to that in a little bit. So this plot is the predictive power of an LD Pareto score. This is again educational attainment, constructed using different sets of SNPs. The bars on the left are genotype SNPs. The middle is HapMap 3, and the one on the right is all imputed SNPs with an imputation accuracy above 90%. So genotype SNPs does much better here because, again, it's HRS and it has 2 million genotyped SNPs. But HapMap 3 with 1 million SNPs also does nearly equally well. And so the blue bars, I'm going to get to that later. Okay, let's see. So more on LD reference data, yeah. The LD reference data should be very representative of your discovery sample. That's the whole point of it. So if you're using a European sample, I mean, if your discovery sample is European, you have to have European LD reference data. I don't know how sensitive it is to minor differences. So it's not going to be, of course, perfectly representative of your discovery sample because your discovery sample is probably is a meta-analysis of like, I don't know, 60 cohorts. But I mean, the same ancestry usually works well. And it should have a sample size, of course, of at least 1,000 is what they give in the LD Pareto paper. So the larger the better, because the LD estimates will be better. And you need to have dropped the related individuals from your LD reference sample, because those are also going to bias the LD estimates. So people, I think, usually don't do this, and I think that's one of the reasons that they say that they don't get as good results as LD Pareto as is claimed. So I think this is an important step. How you do that is you estimate a genetic relatedness matrix using, you could do that, yeah, using genotype SNPs. It's also usually good to drop very rare SNPs.
So we should just say that Matt's going to explain how to estimate a genetic relatedness matrix tomorrow. So that doesn't make sense yet. You know.
And I think it's also in the scripts that Robbie gave or will give you. Right? Okay. So you estimate the matrix and you drop an individual from each pair with that look to be related. You also need to drop ancestry outliers. So the way to do that is you could either plot the principal components and inspect the plots and visually see the outliers and drop them. Or you could estimate identity by state values in Plink. I think that's also in your script, so you're going to see how to do that. And you can check how each individual's distance to his or her nearest neighbor compares to the other people. Yeah.
I was just wondering, I noticed that you used MIF threshold of 0.01 for your GRM, but often, like GWAS pruning, we're using MIF of 0.05. You know, that's just your preference, or is there a reason for the difference?
Yeah, you can do 0.05 too. I mean, you would.
Right, you can put one. So
It doesn't matter that much. I mean, 0.01 or 0.05. You just don't want rare SNPs in there because they would kind of bias the estimates, and you're not very sure about those rare SNPs.
Is how precisely, like, so the problem with the rare things is we don't really have precise measurements of what the correlation is. And so as sample sizes have gotten larger, I think more people tend to push the allele frequency thresholds that we use closer to 1%. And so I think more often when people talk about rare, what they mean is less than 1% now, whereas a paper that came out 5 years ago, rare means less than 5. So it really is just because of how large the samples are in general.
okay.
Yeah. There's a lot more error in the rare SNPs, that's the point.
You can actually calibrate your definition of rare based on your sample size.
Yes.
Because you have 1,000 plus, then 0.01 might make sense, but
Well, it also depends on
it's a smaller sample.
your data. So if it's imputed, for example, I would drop, I would have a stricter threshold, I guess. If it depends on how dense your genotyping chip is and how reliable the rare SNPs are actually measured. So sample size and those things.
Can you explain what IBS is? Because we haven't talked about that.
Can I?
Or maybe just not formally, but just like roughly what you mean by IBS distance.
So it's basically a measure of genetic distance between individuals. I mean, you basically cluster your individuals based on. I couldn't exactly probably say how it's defined.
Well, just
I'm not
looking
sure.
at their genotypes directly,
Yeah.
just estimating how far apart their whole, you know,
What's the S, identity by?
State.
state. So you're not trying to identify how related people are in terms of like, you know, they share the same parents. You're not looking at like a pedigree, a family pedigree. Instead, you're just looking at their genomes and saying how similar are
In
they.
contrast, if you say identity by state or identity by descent, and so state means you just happen to have the same alleles, where descent means that you maybe inherited those alleles from a common ancestor.
So,
When you
yeah?
say threshold of 0.025, does that mean 2.5% relatedness genome?
Yes. No. Yes. Yes. Yes.
In terms
Yes.
of the SNPs that you're using to estimate it, like about, it's about 2.5% sharing. Like on 23andMe, you can get like.
Yeah. I mean, you get the
genome is sharing.
you get the when you calculate the GRM, you get those relatedness distances. Yeah, it's 2.5 per. Yeah, it is 2.
That's what you mean.
Yeah. So we learned what IBS is, and Plink basically clusters individuals based on those IBS values, and then gives you Z-scores that compare your distance to your nearest neighbor versus the average people's distance to their nearest neighbors. And if that Z-score is lower than a certain value, I usually do -5, I think. But yeah, so you drop the ancestry outliers based on that.
Or you just drop one of them, right? If you have two relatives.
Relatives, yeah, this was for ancestry outliers.
Oh, ancestry outliers.
Mhm.
Sorry, I didn't think.
Yeah.
Sorry, what are you calling these ancestry outliers? Because if it's identity by state,
Mm-hmm.
it's not capturing outliers by ancestry, or am I getting that wrong?
What do you mean?
Identity by state's going to be related to identity by descent, but we can't measure identity by descent unless we are looking at big strings of the whole haplotype, and so it's supposed to be an approximation of a person's ancestry. And so if it looks like they're really far, if on average they're just very different from other people across the whole genome, then we say, yeah, these people are probably from a different ancestry.
So in your script, that is, by the way, done kind of iteratively. So you drop outliers, you again calculate the distances, and you cluster individuals. You then again drop the outliers until no outliers remain. So if you're using directly genotyped SNPs, and if you have just the raw data that is not quality controlled, you should do some quality control on that data. Yeah.
In the iteration, does it matter the order, or is this one of those algorithms that is independent of who you drop first?
It is independent, I guess, of who you. Well, I mean, Plink doesn't do it iteratively. It's just in your scripts because I do it iteratively. But I mean, it doesn't matter who you drop first, because in the end you would be left with the same set of people, I think, when you do it iteratively.
There might be really small differences, but I don't think that they're practical differences. I mean, like if you're measuring distance to nearest neighbor and then you've dropped someone's nearest neighbor, then those things might be slightly different. But it's not going to be really large.
I don't think so.
But then if you start with an outlier, then you're basically dropping everyone else, right?
No, so you drop the outlier, and then you recluster, and some other person turns out to be an outlier, and then you drop
Right,
that
but
person
if you
as well.
start with someone who is the outlier, then everyone else is going to be very far from him, right?
Yes.
So you're
That's
going
why
to be
Yes.
dropping everyone else.
Yes.
So then it would be a problem, right, where you start.
Well,
Well,
no.
You calculate the distance to the nearest neighbor for everybody,
When you
Oh,
take
I
the
see.
and
standard
then you just take
deviation,
whoever's the furthest from everybody else.
Okay, I see.
you
Thanks.
calculate the standard deviation, you drop anyone who's more than 5 standard deviations
Yeah.
away from the
Yeah.
mean, and then you repeat. And then the second time standard deviation is going to be something different.
Yes. Okay. So if you're using directly genotyped data and if it hasn't been QC'd at all, you should impose some QC filters. You should filter for call rate on the SNP level, call rate on the subject level, minor relief frequency, Hardy-Weinberg p-value. So you just drop your unreliable SNPs. And the call rate filter is kind of important because you're estimating LD. So if a SNP is only genotyped successfully in like 5% of your sample, you're not going to have a very good LD estimate for that SNP with another SNPs. So it's important to impose a strict call rate filter here.
What are the call rates?
Call rate is, so a SNP call rate is in how many people, or in what percentage of people that SNP is genotyped successfully. So you have non-missing data at that SNP. Subject level call rate is for a person, what percentage of SNPs have been genotyped properly. If you're using imputed data, again, you're going to have to convert your genotype probabilities to hard calls. So some genotypes will be set to missing when you do that, because Plink, for example, has the default 0.1. If uncertainty for that SNP is above 0.1, when converting it to a hard call, it's just going to set it to missing. So I would also filter for SNP call rate after converting the genotype probabilities to hard calls, because you're going to have a lot of missings in your data, and you want to drop those. Okay, LD pred parameters. So there's a fraction of causal SNPs parameter that you have to enter. This is basically analogous to the p-value threshold in the pruning and thresholding. It determines what fraction of SNPs is assumed to be causal in a non-infinitesimal model. So in the paper, they find that the optimal fraction of causal SNPs is 0.3 for schizophrenia, 0.003 for height. So it's not very clear what an optimal threshold would be for a polygenic trait. But for education, for example, 1 seems to be, again, a good threshold. I don't think it would change a lot whether you use 1 or 0.5, as long as it's high enough. So I don't know why it's 0.03 for height. That is a little bit interesting. It may be just a fluke of the data, I think. Do you have any idea, Patrick? No? I would expect a higher threshold for height.
Patrick was calling pi in his slides. P.
Yes.
Yeah.
And if you see an LD pred paper that talks about p, don't confuse it for p-value threshold. It has nothing to do with p-values.
So yeah, for behavioral traits, for polygenic traits, it's generally reasonable to assume that p should be large, because it's a fraction of causal SNPs. So you also need to enter an LD radius. This is also analogous to the LD window in the pruning and thresholding. They suggest the number of SNPs included in your score divided by 3,000. And you also have to enter the sample size of your discovery GWAS. So you only enter one sample size. You don't enter the sample size per SNP. I mean, LDPRED doesn't use sample size per SNP. So it would be nice if you drop SNPs with very low sample size, because it's going to assume that you have the same sample size for those SNPs too, and then there are going to be errors. You could use the median or the mean sample size for that. Conclusion. Okay. Pruning and thresholding is usually, well, it's easier, it's faster, but
Can I ask just one question? So
yeah.
it maybe says, but I didn't see it on the slide.
Okay.
For the summary statistics, do you just need the betas, or what fields do you need? In the
Oh,
data
I
that you
didn't enter
pass
that,
in?
yeah. So you need the betas, the minor allele frequency, the p-value, the SNP IDs, the chromosome and base pair position. You could also have the imputation accuracy. I mean, LDPRED does use it if it's available, but it's not necessary really. What else? That's it.
Can you repeat that, please?
Yeah. So SNP ID, chromosome, base pair position, minor allele frequency, beta, p-value, imputation accuracy, effect allele and other allele, yeah. That's
Question about those inputs. So a lot of consortia don't report all of that information. What do I do if I want to use LDPRED, but I don't have minor allele frequency and I don't have some of those other inputs?
So I think the only problem is the minor allele frequency. They usually report the rest.
Right, right.
I mean, you could just get the minor allele frequencies from 1,000 genomes and use those. It wouldn't be perfect, but it works. Yeah.
Imputation accuracy is also often missing.
Yeah.
And just put a 1. And
Yeah, or NA, something, yeah.
And some of the stuff, like, if all you have is RSID, then you could map that onto.
Yeah, I was gonna
1,000
say, all the
genomes,
time
so.
they don't report the chromosome.
Yeah. So it's
But you
possible
c- yeah.
to get information. My guess is, do they use that just as because that's totally redundant. If you have chromosome and base pair and RSID, is it just a check
Yeah.
or?
I don't know how it. I mean, it doesn't. Maybe it does it by chromosome in parallel, does it? No.
Is it all sort of
So, but I mean, if you have the RSIDs, you could just map it to 1,000 genomes, for example, and get the base pair positions or minor allele frequencies.
do you also sort of use their information to check which sort of if it's HANC 19 or 18 and those sort of different mappings?
sure.
Could you use that?
Well, it has to be consistent with your LD reference data. That's the only requirement, really. I mean, it has to be the same build.
And so and I think that's that's probably why they ask for both, because the RSID kind of in old data may be different than the RSID or in another, or the base pair position for in an old data set might be in a different one depending on the build. And so having both, I think, allows the software to make sure that these things are lining up right. Because the degree to which there's errors and you tell LDPRED that it's one SNP, but it's actually the other, is going to make things fall apart. I imagine it's the same thing with N. I bet you they're using N and p-value as like a sanity check or something, because I don't know why you would need both. I'm not sure what the software actually does.
Do you want to say something?
Me neither.
Inf and p equal to 1?
Inf and p equal to 1.
Yeah, I remember that.
Yeah, so LDPRED produces two set of weights. One is one has this. Well, it says inf in the file name basically, and the other is p equal to 1. Inf is the infinitesimal model. It's the analytical. So I think it's theoretically the same as p equal to 1.
Yeah.
But it is estimated slightly differently.
Yeah. No, so that's what we like. It's strange because if you specify the parameter p equal to 1, you're not going to get a numerically identical result. So if you specify the inf flag or whatever it's called, And
That's-
the
yeah.
underlying theory is the same, so we were very confused by this. It turns out that in one case it uses the analytical formula, in the other case it uses this.
It's very strange that the
MCMC
analytical
procedure.
formula usually does worse. I don't know
Yeah.
why
The
that
analytical
happens.
formula does.
Yeah,
Interesting.
yeah.
But I mentioned it because this business with dropping SNPs to the low end is not really necessary with the analytical formula, right? So there you could just
Mhm.
hard code it and get
That
some.
depends on how they coded the formula.
Right, but we could do it ourselves, I guess. Wouldn't be too complicated.
Okay. Yeah, so pruning and thresholding is faster and easier. But if your clumping R-square is too small, it drops potentially causal SNPs. So you lose a lot of information dropping those SNPs. If it's too large, there's a lot of double counting. But LDPRED, on the other hand, utilizes information from all SNPs, and it adjusts the effect sizes for those SNPs, which is good. But if your reference sample is not representative of your discovery sample, the prediction accuracy might be a little compromised. And the point normal mixture prior distribution that LDPRED assumes may not be accurate for your trait. So these are the scenarios where LDPRED could do worse. But with highly polygenic traits, my experience is that LDPRED is always better. And it's better by, I have a plot here, yeah. So this is EA3. Yellow is HRS, blue is at health. The first four bars are pruning and thresholding with different p-value thresholds. And the last bar, the one on the right, is LDPRED with all SNPs. So this is how much better LDPRED does, which is why we've been saying that you should do LDPRED.
Also because there's just theoretical reasons why it's better.
Yeah. Well, in the end, it's better though. So.
It actually works.
Yeah.
Oh, yeah. So I think people in general do a lot of tweaking with these parameters, and then they choose what gives the highest R-square, and then they only report that. That obviously is not a very good practice. So if you really want to do that, I would at least report everything that I've did, so that it could be just a fluke of your data. If you're just basically, if you do that, you're optimizing based on your validation sample, which may not be the real value of your R-square.
So an example that you might see that is a little bit sneaky, so you might have a person, and we said that you had to pick this p or pi parameter for the fraction of null SNPs as part of LDPRED. And so you might be tempted to say like, okay, well, I don't know what this is, so I'm going to just try a few out and pick the one that's best, because that's likely the true one, right? If the one that maximizes predictive power is going to be the one that's based on the true model, because it's maximizing the predictive power. And so if you then report that, though, you're guilty of overfitting, because there's, again, a winner's curse problem. You're using your same data to fit this parameter, the fraction of causal SNPs, as you're using to say what's the effect of the polygenic score. And so this is, I think, why Aysu is saying, you should probably pick, she says, just do one, or something like that, because even though the right thing may be 0.9 technically, it's important that you make this decision before you start. I mean, you either can cross-validate, which is costly in terms of your data, maybe, or you can just say, well, I'm pretty confident it's going to be one, so rather than wasting data through a cross-validation procedure, I'm going to just pick something that I think is about right. And if your guess is better than the amount of information you're losing by cross-validating, then you'll be better off in that case.
If I remember correctly, if you assume p is 1, then you're saying there's no spikes, basically.
That's exactly right.
So that's a recommendation for highly polygenic traits. That's probably not what we should do for type 2 diabetes.
Okay.
Yes.
So maybe a good strategy would be to register your strategy for deriving the
Yeah.
polygenic score.
I like you.
That's the best.
Do people do that or no?
They usually don't. They usually try a bunch of values and then they report
But you
one.
all should.
Yeah.
Usually people, however, I think usually people do a robustness with just the plain score using all SNPs also. At least that's I think,
yeah, sometimes
what's been
they do,
recommended by
sometimes they don't.
researchers, so I think it's a good idea.
Yeah.
Yeah, be careful how you report that too, right? I mean, like, you want to talk in your pre-registration plan, like, this is our, I mean, like, if you want to test them both, then you need to probably adjust your p-values for that. So you either need to select one that you say, this is my main analysis, and I'm just doing this other thing. Or you can say, I'm going to do both, but make sure your p-values reflect that.
But you could also estimate pi, right, directly from the data. You just use that as your. Is there any reason why?
There are groups that are working on estimating pi.
Yeah.
I don't know that there's sort of consensus on exactly what the right way to do that is.
And how sensitive are the results to choice of pi? If you vary from like 0.05 to 1, does it
It's
make
not
much
that
difference?
sensitive. There's
Yeah.
not much difference. That's why I just do pi equal to 1 for polygenic traits. It's not going to matter that much, really.
In terms of what it looks like in terms of the transformation, just do you mind if I draw some
Of
pictures?
course.
So if we didn't do any, or if pi was equal to 1, then, so this is like the beta from the GWAS, and this is like the weight that you use for the score. So if pi is equal to 1, then it's just going to be a straight line. But as pi gets smaller, what happens is you get something that looks kind of more like this, and so things close to, small values get shrunk more. And then if you choose pi like closer and closer to 0, it looks kind of more like this. And so if you have a pretty well-powered GWAS, then most of the signal lives up here, which is why you wouldn't really expect large differences between one or the other. If your GWAS is not incredibly well-powered, you're going to be living in this region a little more, and so it may be more sensitive.
So it sounds like pi is doing something analogous to what the p-value threshold does in the PGS.
Yeah, it's sort of a smooth version, but this is why we like it. So the reason that we were doing the thresholding before is because we believe that there are SNPs that are contributing more noise than signal, and we say if we think it's contributing this much more noise than signal, then we're just going to throw it out. Whereas LD-pred is kind of doing a smooth version. It's like, well, I don't want to throw it out entirely because there is some signal, and so it shrinks, shrinks accordingly.
Mm-hmm.
So if I'm conducting an analysis with multiple PGSs for traits that have different polygenicity, what should I do then?
Well, so you can have different pi values for different traits. You're just going to construct the scores differently for all the traits in that case.
As far as kind of just a guess that I should do. So the advice has been choose one and go with it.
If one of the traits is pi, if you want to pick pi equal to 1, that would be crazy. So depends on what trait you have in mind.
Okay, so educated guess.
You could also do, if you had access to more than one data, let's say you have access to 2 data sets. One of them is one you want to actually use for your analysis because it has all the other covariates you need for what you're going to do. You could do exploratory analysis in the other data set and find the optimal pi and then use that in your other data set.
Well, one thing to keep in mind though when you do this type of validation is if the set of SNP used to create the score in the first data set, the validation data set is different than the set of SNP you use in the actual analysis data set, the optimal pi might be different in the two. So, so then use maybe the AppMap tree SNP in both data sets to make sure.
Yes. Sorry. Go ahead.
No.
Okay, Lauren.
So one thing I'm always concerned about with polygenic scores is replicability
Mm-hmm.
and transparency.
Mm-hmm.
And I think with all these people constructing all these different things, it's hard. And the one thing about LD-pred is so you're going to get, depending on your reference sample, you're going to get different beta weights depending on all these choices.
Yeah.
How do we as a data user community, she constructs a score and finds a gene environment interaction with this LD-pred score using this reference panel, and I do it with this one and I find slightly different. That could
I think it should be fine as long as you, for example, pre-register your plan, and if you report what you did with the reference sample, how you obtained it, which parameters you used. As long as you report all of that, I don't really see anything wrong with it. It's not going to be reproducible by everyone, but
people aren't going to do that. That's not,
I don't know. I think it's kind of less of a problem here. For the most part, we know that this is a downward estimate of the SNP heritability anyway. So I don't think most people are that worried about whether the R squared is 0.01 or 0.015 or 0.06 versus 0.07.
But I think you're saying you can kind of massage out an interaction and then you have to write another paper.
The polygenic scores may not, so my colleagues and I at Michigan have written a paper on this and looking at a bunch of different polygenic scores and different estimation methods, they may not even be correlated with one another depending on the type of LD. If you use like a top hit score versus, I mean, it might not be, but like especially in this case, I'm just raising that concern.
Yeah,
it's
but
not, I'm not, you know,
I think it's something always to worry about.
Yeah, with any
But-
kind of data.
So my other question, I think this might be that I'm not totally understanding maybe, but so would it be possible for like a consortium to just offer those weights to users already adjusted for these factors using a really robust reference panel, and then that way it gets around a lot of user error, and then users can more easily just throw it into a program like Precise where they don't have to worry about all these other issues that, I mean, are,
Could be done.
and that would help with replicability across.
It's actually something we very much want to do. We're working with some of the data sets now where people, you know, social science data sets where people would want to use polygenic scores, and we're trying to provide consistent, you know, single kind of benchmark score that researchers would use.
This is especially helpful. Oh, go ahead.
But not just the score, but the weights
The weights,
themselves.
yeah.
I mean,
Okay.
so could you provide LD pred weights?
I mean, it could be done using, I don't know, 1,000 genomes as a reference sample, for example. You could adjust, I guess.
There's a subtlety, and the reason why we probably can't provide weights that are as good as scores we can provide is that some of the data come from data providers like, for example, 23andMe, that restrict what we're allowed to make publicly available in terms of the GWAS coefficients.
Sure, no, I understand that. But
Yeah.
just if,
But-
'cause on
But excluding 23andMe, for example, it's
yeah,
I
on
don't
your
see
website
any
you'll
reason.
have the 23andMe
Yeah.
beta weights on there. Could you have beta weights that are LD pred adjusted without 23andMe
Yeah.
data
Yeah,
users?
the cost would be that, you know, it's a smaller N, and so it's going to be less predictive, right? So there's the if you move 23andMe, then our betas are going to be estimated less precisely.
Well, no, sure, but you don't offer those publicly anyway right now, right?
We offer the scores based on.
If we do, yeah, if we do the
Oh, yeah,
scores,
the scores, okay.
it's going to include everything.
But the point you
But in
raise, I think, is
principle,
very important.
yeah.
It's something that came up at the LA conference, and there is a real risk that as these things become more predictive, we'll see another wave of kind of candidate genes studies that don't replicate very reliably, and we need to think about how to deal with that. I think like adopting a uniform set of standards is useful. Harmonizing how we report effect sizes, or pre-registering, being transparent about pre-testing, all of those are good things. You know, relative to the candidate genes, these things are at least 100 times more predictive. So Matt's right; it's less of an issue, but I'm sure that there'll still be abuse and nonsense.
And like we'll all be reviewing. So like, you know, to some degree, it's like we need to enforce these kinds of things.
You guys, your responsibility.
Yeah, you meaning all of us in this room, right? Because like you should be pre-registering yourself, and if you're receiving papers to review, and it looks like they haven't pre-registered, and it looks like there's evidence that they were jimmying with things a little bit, then you should be like say, oh well, you know, what did you know, how many things did you try before you get here? And I think that we should give a lot more credit when it's been pre-registered versus when it's not been. And so these are things to maybe watch for as you're consuming and producing your own research.
I think actually pre-registration is, maybe we should talk about this more in detail later actually. It's a good idea to pre-register, I think in general. I think whenever there's several layers in the analysis, then it becomes difficult to plan ahead everything, but that's not a discussion. Whenever it's simple enough analysis, I think there's no excuse.
Any other questions about scores?